So we are looking at shortest paths and weighted graphs. And we said that there are two types of problems that we might look at in terms of shortest paths. The one that we have looked at already is the one which is called the single source shortest path problem, which asks you to find the shortest path from some designated starting vertex, source vertex, to every other vertex. And we imagined two scenarios where this might be useful. So if you have a kind of factory which is shipping out finished products to retail outlets, or if you have a courier company which has got a centralized delivery facility from where they have to ship out their things for delivery. Both of these would like to know the shortest route from wherever they are shipping out things, either the finished product or the courier deliveries, to all the other locations in their transportation graph. On the other hand, another natural problem is to find the shortest distance between every pair of vertices. And this we said would be very natural if you're running something like a travel site. Somebody wants to book a ticket from somewhere to somewhere else. You should have the information about the shortest route from this starting point to the ending point, regardless of which 2 points they are. So you can't say I am only booking tickets from this city and not from another city, right? So that doesn't make any sense. So if you have a travel booking site, it should be able to give you optimum routes in terms of cost or time or distance or whatever from anywhere to anywhere. So we have seen two algorithms for the single source shortest path problem: Dijkstra's algorithm, which works if there are no negative weights, and the Bellman-Ford algorithm, which works even if there are negative weights. But of course, remember that negative cycles are always forbidden, because with negative cycles, the whole thing doesn't make sense at all. The idea of a shortest path is meaningless. So how do we find all pair shortest paths? So we can find the shortest path from a single vertex to every other vertex. So we can just iterate this by starting it from every vertex, right? So I started from 0, I get all paths from 0. I go to 1 and I started from 1 and I get all paths from 1. If I do this n minus 1 times, I will have the shortest paths from every starting vertex to every ending vertex, right? So this is one way we could do this, is just to repeatedly run Dijkstra or Bellman-Ford across all starting points. But what we are trying to see is whether there is another way to do this which doesn't involve this kind of going back and restarting the calculation. So that's what we will look at in this lecture. So we will begin with something that we saw earlier, namely the transitive closure. So remember that the transitive closure we discussed in the context of unweighted graphs. And we said that transitive closure actually is the reachability calculation. So we wanted to find out, just like all pairs shortest paths, we wanted to find out all pairs reachability. Given I and j, can I get from I to j in this graph? Is there a path from I to j? So again, there we said that we could have run BFS or DFS from every starting vertex and got it, but instead we ran this other algorithm which used this matrix approach, right? So we started with this adjacency matrix, and we said that an adjacency matrix represents implicitly edges which are paths of length 1, and then we wanted to use this matrix and an operation of matrix multiplication to bootstrap this from lengths of 1, paths of length 1 to paths of length 2 and so on. So we said a path of length 2 decomposes as 2 paths of length 1. So if I want to find out the path of length 2 from I to j, I just have to check for some intermediate k whether I can go from I to k in one step and then from k to j in the another step. And we can generalize this, and we discussed why this is matrix multiplication. We can generalize this to L steps. So if I know how to get in L steps from I to j, then I know how to get in L plus 1 steps from I to j, because I go to an intermediate k in L steps and then from k to j in one step. Right? So by decomposing L plus 1 steps as L steps followed by one step, I can again do a matrix multiplication and do AL times A is equal to AL plus 1. And finally, in the transitive closure, we want to look for a path of any length, but paths, remember, are always bounded by length n minus 1, because there is no need to go through a loop to reach something. So it's sufficient to calculate path lengths 1 to n minus 1 and then take this sum, right? The sum, if you remember, was the OR. Right? We said that this is the OR of, so if there is a 1, if Aij is 1 in any of these matrices, then there is a path of length 1, 2, 3 or up to n minus 1, and therefore A plus Ij, the transitive closure, reports 1. So we are going to slightly reformulate this calculation of transitive closure. So we are going to do, so this is a kind of inductive definition, right? So we first find transitive closure by first finding paths of length 1, paths of length 2 and so on, and then we take the cumulative effect of all this by doing the plus at the end. Now we are going to do another inductive thing, but we are going to use a slightly different way of calculating simpler paths and complicated paths, not in terms of path lengths, but which vertices we go through. So we'll, just to distinguish it from the earlier one, let's call it B. So earlier we had A sub A to the k, right? If I said A to the k I comma j, right. So this was referring to paths of length k. It says that there is a path of length k from I to j, right. So here I have something else. B k I j does not refer to the length. It refers to which vertices I am allowed to visit on the way from I to j. I am not obliged to visit all of them, but I can't visit anything outside the set. So if I say k as my superscript, it says I am only allowed to go through vertices 0 to k minus 1. I am not allowed to visit any other vertex going from I to j. So if I have this constraint, can I reach I to j? So it could be a direct thing in which I don't go through anything. It could be 3 of these vertices, it could be 2 of these vertices, it could be any number, but it cannot be outside this set. Now remember, it's going to be a path, so I'm never going to visit a vertex in this set more than once, but that doesn't matter so much. It's just telling me that I can get from I to j without going outside the set 0 to k minus 1. Right? And this constraint of course applies only to the vertices I visit in between. So I and j need not be between 0 and k minus 1. I could be anything, j could be anything. Right? So I'm just saying that when I leave I and before I reach j, in between I should not see anything which is outside the set 0 to k minus 1. So in this setting, what would b of 0 mean? So b of 0 by this definition would be some 0 up to minus 1 because k is 0. So this is basically saying that I am not allowed to visit any vertex in between, because the set of vertices I visit in between can have at most number minus 1, but I know that my vertices start with 0. So there is no vertex in the set which starts between 0 and ends before minus 1. So therefore b0 ij basically says that I cannot have any intermediate vertex, because no intermediate vertex can satisfy this constraint that its index is minus 1 or smaller. So therefore b0 of ij precisely captures the fact that I can go from I to j without visiting an intermediate vertex, means there is an edge from I to j. So b0 is just my adjacency matrix A. Right? So just like in the earlier case, we started off with paths of length 1 and we said paths of length 1 are precisely our adjacency matrix A. Here we are saying paths which do not pass through any intermediate vertices are exactly captured by our adjacency matrix A. So the starting point of this induction is A in both cases. So how would we proceed? Well, I want, like before, I want to calculate what would be bk plus 1. So bk plus 1 says that I am allowed to use 0 to k. Right? So if I am allowed to use 0 to k from I to j, then there are two possibilities. One is that I don't need this k at all. I could already do it without 0 to k. Right? So that means that bk of ij is already 1. It means that without going to k, just staying within 0 to k minus 1, I have a possibility of going from I to j. Or I need to use k, right? But if I need to use k, then remember now we use this property that was implicit, that we are going to visit k only once. There is no point in visiting k multiple times. So if I need to use k, I need to get from I to k and I need to get from k to j. But if I am using up k and going from I to k, then I cannot be using k in between, right? I am using k only once overall. So going from I to k, I don't see k. Going from k to j, again I don't see k. So I can find out whether I can go from I to k using only the vertices 0 to k minus 1. And similarly, whether I can go from k to j using only the vertices 0 to k minus 1. And then I can pick these two paths. So I have a path from I to k and I have another path from k to j. And now together these gives me a new path from I to j which visits k. Right? I am forced to go to k, but in between I don't do anything outside 0 to k minus 1 except when I hit k. So this is my condition now. So I say that bk plus 1 ij is 1, either if it is already 1 in bk, so bk ij is 1 means I don't need k, or I go to k explicitly, in which case I go from I to k in bk minus in k minus 1 using k minus 1 vertices, vertices up to k minus 1, and then I go from k to j using vertices up to k minus 1. Right? So this gives me the inductive calculation, and this is a different way of calculating the transitive closure. So this particular algorithm is the more standard algorithm that you see in books, and this is called Warshall's algorithm. Right? So this is Warshall's algorithm. So we use the other algorithm because it's nicer in terms of describing why it is matrix multiplication. So this requires a little more work to put it in that framework of matrix multiplication, but essentially it's capturing this inductive property of finding more and more complicated paths. So here the complication is the number of which are the different vertices you have to see in between, rather than the total number. The total number is what the other one is talking about, the length of the path. Here it's restricting you to some subset of the vertices, and that subset keeps growing. Eventually you can use all the vertices, right? So this is the thing on the right formally now. So b0 of ij is just aij, and bk plus 1 ij is 1. If either bk ij is 1, so we already can get from I to j without using the kth vertex, or bk ik is 1 and kj is 1. Right, so this should look very familiar because it looks very similar to the other one. Just the interpretation of the superscript attached to the matrix is different. So in this now, when do we stop? Well, when the superscript becomes n, it says I'm allowed to use any vertex from 0 to n minus 1, it should be, right? I'm allowed to use any vertex from 0 to n minus 1. That means I'm allowed to use any vertex at all. That means there is no constraint, so I have some path or the other. So if I do this up to bn, so in the earlier case also I did it up to a1 to an minus 1. So here if I do it up to bn starting from b0, then I am done. So bn is the same as a plus, and now what we are going to do is we are going to see that this shortest path algorithm that we have, not the shortest path, this transitive closure algorithm that we have due to Warshall is actually very easy to extend to the shortest path problem for all pairs. So remember that transitive closure is the equivalent of all pairs reachability. Right? Dijkstra's algorithm is the equivalent of BFS, except that we have weights. So weighted reachability is Dijkstra. Right? Now weighted all pairs reachability is all pair shortest path. So we are going from transitive closure, which is unweighted all pairs reachability, to weighted all pairs reachability. So with weights we are asking what are the shortest paths. So we will use a similar notation. So let's call SP for shortest path. So shortest path with superscript k between I and j is the length of the shortest path provided I stay within vertices 0 to k minus 1 when going from I to j. Right? So that's what this means. So earlier it was saying that there is a path. Now I am saying among the paths that are there, what is the shortest length? I am keeping track of the shortest length. Not just the fact that there is a path, but there is actually a path of minimum length. I am keeping track of that minimum length. Right? So what is the base case? Well, if there is no possibility of going through an intermediate vertex, then we saw that b0 of ij was just aij. In this case, I don't want the edge or not edge. I want to know the weight of the edge. So sp0 of ij is w of ij. Remember that w is our weight matrix. So w tells us for each edge what is the value, right? So wij is the weight function. So wij tells us how much cost is there with this edge. Now, of course, we have to take care of the fact that there is no cost and no edge carefully. So what we will do is we will assume that when we have no edge, actually the weight is somehow assigned to a very large number. In particular, we can treat it mathematically, we can treat it to be infinity, right? So if there is no edge, sp0 ij will report infinity. If there is an edge, it will report the weight of the edge. Now the update rule is slightly different from the transitive closure rule. So this is the slight tweak that you need. So either I can go from I to j without using k. So sp k plus 1 ij is either sp k ij, or I go using k and then I have to check the cost. Now earlier I just wanted to check whether this was there or that was there. I just needed to do the logical or. Either I can go without k or I can go with k, and I take the or. Here I have to say how much does it cost me to go without k and how much can I gain by going with k, right? So I either take the cost of going with k, which is the shortest path to k from I, followed by the shortest path from k to j, right? Or I take the shortest path without going through vertex k at all, and I take the minimum of these two, right? So this is my update rule for the shortest path matrix. And as usual, so this again this same typo, but the shortest path matrix, if I now calculate up to the nth step, then it will tell me the shortest path among all paths, the length of the shortest path among all paths that go through any intermediate vertex from 0 to n minus 1, right? And that covers all possible intermediate vertices. So this will be the overall shortest path from I to j. So this particular algorithm is called the Floyd-Warshall algorithm, right? So the original algorithm for transitive closure is due to Warshall, and Floyd is the person who adapted this algorithm for shortest paths, all pair shortest paths. So jointly it's called the Floyd-Warshall algorithm. So let's go back to this graph which we have seen before. So this is a graph with directions and with negative vertices. So I have these negative edges. So I have some negative edges here and there, right? So now sp0 is basically the adjacency matrix of this graph. Is basically a of ij, where I replace at every entry the weight, right? So if I look at 0 to 10, 0 to 1, it has weight 10, for instance. If I look at 4 to 5, for instance, it has weight minus 1, and so on. right? So this is just the adjacency matrix for this graph, where every entry ij represents the weight, and if there is no edge, then it's infinity. So we have a lot of infinity entries, we have very few entries which are not infinity. So now what is SP1? So SP1 represents all things that you can reach going through the set 0. But look at 0. See, 0 has no incoming edges. I cannot go to 0 and then go from 0 anywhere, because 0 is such that you can only go out from 0. So I can't go from I to 0 and then 0 to anywhere. So intermediate 0 as an intermediate vertex is not useful in this graph. There is nothing I can go to via 0. So therefore SP1 is actually the same as SP0. That is, if I am allowed to go through 0, I gain nothing. Right? If I am allowed to go through 0, I gain nothing. So this is a subtle difference between this and the transitive closure thing. So there are paths of length 1, and then there are paths of length 2. But the paths of length 2 cannot go through 0, because if I go through paths of length 2 through 0, I have to enter 0, and I cannot enter 0 because the directions are all pointing out of 0. Right? So in this case, the first iteration produces no change. Now, this was my first iteration, so this is SP1, which I just calculated is the same as SP0. Now I want to calculate SP2. SP2 tells me I can go through 0 and 1. Haha, so now I can go through 1. So there are edges which come into 1. Right? So where can I go by going into 1 and then out of 1, because I can't go back to 0 anyway. So I can go, for instance, from 6 to 5 via 1, right? Or I can go from, say, 2 to 5 via 1. So these are two of the things that I should get new, and indeed when you see that, you will see that I get from, so the three incoming edges are 0, 6 and 2. These are the three incoming edges to 1. So these give me new possibilities of going from 0 to somewhere, from 2 to somewhere, and 6 to somewhere, but the only thing I can reach from 1 is 5. Right? So all the updates happen in column 5, because that is the target. So from 0 to 5, I now find that there is a shortest path, which is 10 plus 2. Okay? So I go 10 and then 2. Similarly, from 2 to 5, I find the shortest path, which is 1 plus 2 is 3. And similarly, from 6 to 5, I find the shortest path, which is minus 4 plus 2 is minus 2. Okay? So this is my first update. Now let's do one more update. So I have now shortest path. So these were the updates which I got when I did the first update, right? And now I have discovered that I can reach 2, I can reach 6, and I can reach 5, right? No, sorry, the new thing I have discovered is I can reach 5. So now I have to see what all I can reach from 5. So from 5, for example, I can go back to 2, but from 2 I can go to 3 and so on. So in the next round, I actually get a lot of updates, right? So I get updates from 5 to 1, because now I can come to 5 and then I can go to 1 using minus 1. And so why is that the case? Because I can actually go around this way, right? So I can go up and go this way, right? And this gives me minus 2 plus 1, which is not the one I want, I think. 5 to 1. Yeah, minus 2 plus 1 is minus 1, sorry. Yeah, that's the one, right? So in this way, I can now update everything one more time, and I can keep doing this. And if I do this now, there are 8 vertices in this. So if I do this up to b to the power 8, then I will have all paths which go to 0 to 7, and you can work it out. I'm not going to work it out. You will get a matrix which gives you all the shortest paths from everywhere to everywhere. Right? So this is the Floyd-Warshall algorithm. So to summarize, we started with Warshall's algorithm. So Warshall's algorithm is an alternative way to compute transitive closure. So it's an iterative transitive closure algorithm. Earlier we did it in terms of lengths of paths, and now we have done it in terms of which intermediate vertices I'm allowed to visit while traveling from I to j. So that's the difference between Warshall's algorithm and the way we had formulated in terms of paths of length 1, 2, 3 and so on, right? So bkij is 1 if I can only reach I to j using only vertices 0 to k minus 1, right? So when we adapt Warshall's algorithm for shortest paths, what we basically do is we replace that calculation of or. I can either reach it without using k, or I can reach it with using k. I replace that or by minimum. What is the minimum I can do without using k? What is the minimum I can do with using k? And I use that to update this thing from I to j, right? So this is called the Floyd-Warshall algorithm, and it should work, as we saw, with negative weights, provided there are no negative cycles.